Hi, my name is Jake Bergquist, and today I'll be talking to you about improving the localization of cardiac geometry using ECGI.
Electrocardiographic imaging, or ECGI, is based around the principles of using the physical relationships between how an electric source from the heart propagates to the body surface, and then inversing this relationship in order to calculate the cardiac source potentials given a body surface recording. Several ECGI systems have emerged clinically and have been used to great effect to diagnose and treat various cardiac dysfunctions using this non-invasive diagnostic method. However, ECGI is still plagued by a number of controlled and uncontrolled error sources. One of the most notable of these is errors in cardiac position in the ECGI model. The forward model takes in the geometries of the torso and the heart, as well as their relative conductivities, in order to construct the forward transfer matrix A. And changes or errors in the cardiac position can have drastic effects on the forward model output. Let's take a look at an example here where we have a cardiac geometry and the extracellular potentials measured during the peak of the QRS mapped onto it. Let's see what happens to the predicted forward model results on the torso surface as we move this cardiac geometry to different locations within the torso. Notice what a drastic effect changes in the cardiac position can have on the forward model solution. Let's take a moment to watch that again, both observing the changes in the cardiac position and the resulting changes to the forward computed body surface potentials. Because the accuracy of the inverse solution is highly dependent on the accuracy of the forward model, errors in cardiac position such as this can have drastic effects on the inverse result.
These effects can be amplified by the ill-posed and ill-conditioned nature of the inverse problem. Therefore, accurate reconstruction of the cardiac geometry is imperative for ECGI solution accuracy. There are several different sources that could cause geometric error during either an experimental preparation or a clinical setup. For example, when the patient breathes, their heart is going to move as their chest expands and their lungs fill. Remember, as we saw here, movement in the heart can cause differences in the torso potentials that may not be accounted for in the geometric model if it's based off of a single static image. These geometric errors can be quite difficult to correct using procedural changes. For example, it can be difficult to attain additional imaging that captures the motion of the heart, and it can also be impractical to require that the patient or subject maintain some sort of breath hold procedure during recording. Therefore, there is a need for a method or some sort of framework to remove all of this cardiac localization error, ideally using some sort of non-invasive measurement technique.
Previous developments by Drs. Coll-Font and Brooks have developed a method to correct for the cardiac geometry by leveraging the ECGI forward problem. This method uses measured body surface potential and electrogram data in order to compute the difference between simulated and measured body surface potentials, and then use this difference in order to correct for the cardiac geometry. The following visualization demonstrates how this method works. On the far left, we have the cardiac source. Next to that is the forward computed body surface potentials. On the far right, we have the measured body surface potentials at that point during the beat. And in between the measured and computed body surface potentials is the difference between the two at the measurement locations. We can see that as we move the cardiac position away from the correct location, the error between the forward solution and measured body surface potential increases. However, if we move the cardiac source closer to the correct location, the error decreases. By developing an optimization framework around this that minimizes the difference between the forward computed and measured body surface potentials, we can optimize for the cardiac geometry. In order to do so, the position of the heart has to be parameterized into a lower dimensional space. We can describe the position of the heart using 6 degrees of freedom: pitch, yaw, roll, X translation, Y translation, and Z translation. Here, roll is defined along a septal axis. Let's watch all of those again from a different perspective. Pitch, yaw, roll, X, Y, Z. The method developed previously relied on having access to both body surface recordings and recordings of the cardiac source itself in order to perform this forward-based optimization. Here in our research, I would like to propose the extension of using only body surface potentials in order to correct for cardiac geometry using a similar optimization scheme. In order to accomplish this extension, we need to make a few assumptions. If we look at the original method, this was some sort of optimization function that took in torso potentials and the heart potentials, as well as a forward transfer matrix A that depended on the position of the heart for any given beat, PB. In order to extend this method to where we only have the torso potentials, we need to, instead of using the cardiac source potentials, use an inverse estimation of the cardiac source potentials. However, this presents a potential problem of overfitting. To address this, we include additional information in the problem, such as including multiple heartbeats recorded from the torso surface, and assuming that each of them have the same cardiac source potential distribution. We then iteratively estimate new inverse solutions and new cardiac positions for each of the heartbeats considered. In order to assess the performance of this novel method, we generated a synthetic data set using data collected from a torso tank preparation. We took the cardiac geometry, represented here as a pericardiac cage consisting of 256 electrodes, and artificially moved it to different locations within the torso tank. We then took a single ventricular paced beat recorded at that pericardiac cage and forward computed body surface potentials for each of the positions. We then added Gaussian noise to a signal-to-noise ratio of 30 and considered these to be our measured torso potentials. This resulted in a data set of 100 heartbeats with different cardiac positions and measured body surface potentials, all of which were forward computed from the same measured cardiac source. We then reconstructed the cardiac position using our novel method by inputting all of the body surface potentials for each of the beats and a single nominal cardiac position or starting position for all 100 beats. In order to assess the performance of our novel method, we measured both the ability of it to reconstruct the cardiac positions accurately and how much it improved ECGI solutions over using the nominal unoptimized cage positions. Here you can see the reconstructed position parameters in red as compared to the ground truth parameters in black. We see very good agreement between the reconstructed and ground truth parameters. We assess the geometric reconstruction accuracy by comparing the distance between the centroid of the ground truth cage locations to the optimized cage locations. For comparison, we also show this calculation for the initial unoptimized positions. We then calculated the average electrode by electrode localization error. We also visually compared the ground truth locations to the optimized locations. The ground truth position is shown in blue, and the reconstructed is shown in red. As you can see, our method was able to reconstruct the position of the cage for each heartbeat with a minimal offset that appears to be somewhat constant throughout all of the beats. We assessed our method's ability to improve ECGI solutions by calculating a solution using either the ground truth cardiac location, the optimized cardiac location, or the initial cardiac location. We then compared ECGI solutions to the ground truth cardiac source, using either temporal correlation, spatial correlation, root mean squared error, or visual inspection. As we can see, optimization resulted in drastically improved inverse results as compared to the unoptimized case, although the results do not perfectly match using the ground truth geometry. We suspect that this is due to the lingering geometric error. Let's take a moment now to compare the inverse solutions that we're seeing. If we go ahead and pause right in the middle of the QRS, just about here, we can clearly see that the optimized position and true position produce far superior reconstructions than the initial unoptimized position. Not only is the spatial distribution very different on the initial position also shows maxima and minima values that are far outside the range of what's being observed in the measured electrograms. In the future, we plan to refine this geometric optimization framework by including additional constraints, such as mandating that neighboring beats have similar cardiac positions. We also plan to apply this method using real data sets from both our in situ experimental prep, as well as our other torso tank preparations in which the cardiac position was actually modified during recording.
The ability of this method to reconstruct cardiac position using only body surface measurements represents an opportunity to improve all ECGI formulations. Because no invasive electrogram measurements are required, this can be applied to both clinically and experimentally to improve ECGI solution accuracy. Scientific progress is not a one-person job, and I would like to take this time to thank all of the people who have helped me along the way. I would like to thank my mentor, fellow graduate students, and all the support staff at the Cardiovascular Research and Training Institute and the Scientific Computing Institute, as well as my collaborators and mentors, and of course my funding agencies. Thank you all for your time.